Hi, I'm Derek May West, and this is Josh Kohler, and we're with Gemstone's Team Rio, and today we're going to talk to you about private or symmetric key encryption, as it's more commonly known. Private key encryption is a very strong encryption algorithm. It's impossible to crack unless you know the key that the end users both have, which we'll explain in a few moments, which makes it very advantageous for mission critical or absolutely essential data. But there is one large caveat to it. So, Josh?
All right, we feel the best way to explain to you guys what private key encryption really is through an example. So let's get started. All right, so let's imagine that we have two people named Alice and Bob. And let's say, just for the fun of it, that Alice and Bob are located far away from one another, and they want to share private messages. They can use private key encryption to do so, as this technique allows secure messages to be sent to other parties. In fact, there's actually an historical precedence for using private key encryption to send messages. That is, the infamous red telephone in the Cold War, which connected the Soviets in Moscow with the Americans in Washington, D.C.
Okay. So let's say that Alice and Bob want to share a message, and we'll call that message M. It's not really an envelope, but let's signify it as such. And we want to share it securely. So we'll call the message M and the key K. The key is a predetermined string of binary bits, and binary bits are just zeros and ones. So let's generate a key. Let's say 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, dot, dot, dot. So the key goes on. And the message that Alice is going to try to send to Bob is going to be 6 bits long. Let's say it's 110101.
And so what you want to do with private key encryption is you're going to actually XOR the message M with the key. Specifically XORing M with the key's first M bits.
So in this case, 6 bits, right?
Yes.
So the XOR operation, if you know anything about binary operations or about digital logic, the XOR operation is similar to the OR operation. The OR operation in digital logic goes something like this. If you have 2 bits that you're ORing together, an X and a Y, you're going to get an output. So let's say 0, 0, 0, 1, 1, 0, and 1, 1. When both bits are 0 or both bits are 1, well, when both bits are 0, the output is 0. When you have a 0 and a 1, the output is 1. When you have a 1 and a 0, the output is 1. And when you have a 1 and a 1, the output is 1. So basically, the OR operation sees if there's a 1 between either X or Y, thus OR, and if there is, then the output will be 1. XOR is similar, but different in one case only, and we'll show that right now. XOR stands for exclusive OR, which you'll see why in just one second. So let's set up the same table as we did before. And the outputs for the first few remain the same, 0, 1, 1, but the last one is different, and here's why. Exclusive OR says that there should be only one bit between the two inputs, X and Y, that's 1. So for 0, 1, there is 1, 1, and that's Y. The output is 1, therefore. In this case, there's 1, 1 between X and Y, and that's X, and the output is, again, 1. But in the case of 0, 0, or 1, 1, the output is 0 because there are either no 1s or more than 1, 1. That's the XOR operation. So let's XOR these bits. Does that look right, Josh?
Yep, that's correct. And so now what Alice wants to do is once she's generated this encrypted message, is she will throw away the N bits of the key because she no longer wants to use them. Make a nice little trash can there to throw them away.
Or recycle them. Well,
Or-
no, not recycle. Just garbage.
Garbage, alright. And so, now that the message is encrypted, it will be sent over to Bob. Now remember, Bob has this same key. And so in order to decrypt the message that Alice has sent him, what he will do is he will once again XOR the encrypted message from Alice with the first n bits of the key. And Derek will go ahead and demonstrate this for you.
So again, we have Bob's key, which is the same as Alice's, and we have the message, which is encrypted, M sub E. So now we're going to XOR these. And 0 and 1, that's 1. 1 and 0, that's 1. 0 and 0, that's 0. 0 and 1, that's 1. 1 and 1, that's 0. And 1 and 0, that's 1. And as you can see, the output of the decryption is the same as the input for the encryption steps. In other words, the message is identical.
So now we have securely transferred messages between Alice and Bob.
Oh, and Bob also throws away his bits to the key once he's finished decrypting, because Alice has thrown away hers as well, and the next time they talk, they'll use the next bits in their encryption key. So now it's time to talk about the one big caveat of private key encryption. Private key encryption sounds great on paper. In fact, it sounds excellent. It sounds like exactly what our security community needs every day. However, the one big caveat is this. You remember when we talked about the key. The key is predetermined, as we said, and the predetermined key is exchanged at a time and a place that is convenient for both parties before they know that they're going to be exchanging encrypted information. So they might put it on a zip drive or a floppy disk in the old days, and they would have their spies or their allies exchange it with one another at a discrete location. Now, that sounds great, but if someone wants to make an anonymous connection, for example, if you're online and you're sitting at your computer and you want to buy something. It's a great chair. If you want to buy something online, shopping bag, not padlock, you want that transaction, your credit card data that you're sending over the internet to the online retailer to be secure. However, the problem with using private key encryption or something, well, the problem specifically for using private key encryption with this is if you had a big box retailer that you were trying to exchange data with or get your credit card information to via private key encryption, you would have had to get a key generated and exchanged with them before you made your transaction online.
And unfortunately, if, let's say, we like to shop at Amazon, there isn't a customer representative just for us that we can generate this key in exchange with. So it's very impractical to use private key encryption.
Which is why we did another blog a little bit earlier about public key encryption, which was created by some very intelligent mathematicians, which, though it is not completely perfect like private key encryption, it relies on the thought that computers are restricted to a certain speed, and although private key encryption can be broken, it's impractical for the amount of computing power that it would take and the amount of time that it would take to worry about the security concern of it being broken.
All right, and that pretty much wraps it up for private key encryption, right, Derek?
I think so.
We hope you enjoyed our presentation on private key encryption. And who knows, perhaps you can use it later on down the road to send secure messages of your own. And if this interested you, we'd also like to point out that you can follow us at teamrio.blogspot.com for more cool posts. We'd love to have you.